Sorry about that. We started talking about different types of systems, and we talked about linear shift invariant systems. And in particular, I mentioned the convolution property. And the convolution property is extremely useful because if I have a linear shift invariant system and I put an impulse through the system, what do I get? What do I get if I put an impulse into a system?
Impulse response.
Impulse response, yeah, absolutely. And this is by definition what an impulse response is the response of a system to an impulse. Now, in the case of linear shift invariant systems, the impulse response is kind of its DNA. It really characterizes everything that you want to and need to know about that system. It basically tells you everything. And that also means that if I, let me just pick up the spotlight here. That also means that if I put a arbitrary input into the system, I can compute what the output is going to be just by knowing the impulse response. And the output is going to be the convolution between the input and the impulse response. So no matter what g of x is, I know exactly what the output is going to be if I know the impulse response. So this is very, very powerful, extremely powerful property, because it basically let me either predict what the output is going to be, or it can assist me in designing certain inputs such that the output would be as close as possible to what I'm interested in. Okay. Now, I did mention that convolution is generally a blur. I mean, it could make things, sharper if it's a high pass filter, but it's generally a blur. And for example, if you have this a rect function convolved with a rect function, it's going to be spread twice as much. So if this is a width of 1, this is width of 1, then this, that function is going to spread into a width of 2, which is pretty much what a triangle is. Okay, so that's so this is the convolution. Okay, so now let's move on into the Fourier transform, and in particular the Fourier transform in one dimension. And this is really the form that we're going to be using in class. So first of all, note that things are maybe slightly different than what you typically used to. If you think about it, normally you'd have like an F or omega or all that kind of stuff. So the frequencies that we're going to be dealing with, or the spatial frequencies, we're going to call them K or Kx, or in the general case, it will be a vector of K, which will be the frequencies. And the definition of the Fourier transform is the following: is integral from minus infinity to infinity of the function x multiplied by this Fourier kernel. And this Fourier kernel e to the minus j 2 pi kx times x dx. So effectively, this transformation transforms f up from being a function of x to being a function of kx. All right. Now, if you stare at this long enough, you can kind of see, oh wait, this kind of looks like an inner product. Just by definition of usually inner products, is that you take this complex exponential, which is a frequency, right? This is a frequency. And then you multiply it by f of x and then integrate over. That's by definition inner product. So the results of these f of kx's are different inner products of the function f of x with the different frequencies. So pretty much projecting onto the Fourier basis. Okay. So this is the Fourier transform. Anybody have not seen this in this type of form before? Feel free to put your camera on so I can get a little bit of a, oh, what is J? That's interesting. Who said that?
Me. Christine.
Hey, Christine. Yeah, Christine, which department are you?
I'm in neuroscience, and so I work with mice, and I managed to not take like any math classes in college. So I
Oh, wow.
Probably. Yeah, I can withhold many of my questions, but I'm just, yeah, trying to learn via osmosis and immersion.
Okay, so quick question. Complex numbers, I'm sure you're familiar with.
Yes.
So what is the square root of minus 1?
I.
I. So J.
Yeah.
So J in electrical engineering is an I in math.
Okay.
And the reason is and the reason that we sometimes in electrical engineering you use J, and this is, I put J here, but it could be an I, for all its sakes. The reason that electrical engineers use J is not to confuse with I for current, because that's really the only reason. But thanks for asking that. I really appreciate it.
Thank you for explaining.
It's I in the textbook. So I was wondering too.
Okay. Yeah. So let's just so I'll switch. I'll switch to the I notation. Okay. So. And then we'll just use I. But basically, I just because I teach many classes. Every class is slightly different. Like DSP would be J, some other one would be I. So like we'll just switch those interchangeably. In fact, in MATLAB or even I think Python, if you write one J or one I, that's the same as an I. So it doesn't really matter. Okay, so this is the forward Fourier transform. It's taking f of x and projecting it onto those complex harmonics. Now, the inverse Fourier transform is doing exactly the opposite, is more as a synthesis, right? What it is you take the spectrum f of kx and then you multiply it by a Fourier kernel, but the only difference is that now it's conjugated, so it's a plus j. 2 pi kxx, and now the integral is over kx as opposed to here being over x, and then at the end we get the function f of x. This is a one-to-one relationship, so you can go back and forth without losing any information whatsoever, which is pretty amazing. Now, for those of you who are familiar with another form of Fourier transform, we have an omega here, not 2 pi k. Then the nice thing I think about actually having, so the only difference is that the omega is angular frequency, whereas here k is actually a frequency. Okay, so not the angular frequency. And so it actually has a unit kx. And the units are, well, we'll talk about that in a second. The nice thing about actually using 2 pi kx is that the forward and inverse Fourier transform here are symmetric. They look the same. If you wanted to use omegas, then the inverse and forward are not going to be the same. There needs to be some scaling operation. I think divided by 1 over 2 pi or something like that. So I think that's what's nice to think about this. And also it's very easy to think in terms of these units of k, and I'll just get to that. So actually, what will be the units of k?
1 over whatever the units of x are.
Ah, nice. Smart. Yes, it's 1 over whatever the unit of x. So if x is seconds, then kx would be hertz. Hertz. Yeah, hertz in units. And then if x is centimeters, then what would be kx?
Inverse centimeters.
Yeah, inverse centimeters, absolutely. Yeah, isn't that pretty simple? Okay, so yeah. So if x is in centimeter, kx is in 1 over centimeters. And I like to think in those type of units. Centimeters and 1 over centimeters are great units to think of. Okay, so Fourier transform has, there are definitely, like, you don't need to compute this integral over and over again. In many cases, there are some functions that we know exactly what their Fourier transform is. And so here are some important functions. If you remember the rect function, what's the rect function defined as?
It's 1 between -1/2 and 1/2, and 0 elsewhere.
1 between -1/2 and 1/2. and it's and then 0 elsewhere. That's right. And so in that case, the Fourier transform would be a sinc. Okay, sinc, which is sine of pi k divided by pi k. Okay, so it would be a sinc. So a rect becomes a sinc. What about a constant? So a constant, if you have something that's constant, it's basically, you know, 0 frequency, if you think about it. So from a frequency content point of view, it only lives at 0 frequency and not with anything else, right? It's just constant. In that case, the Fourier transform of it will be an impulse function at k equals 0. Right? Because if we compute the frequencies of something that's constant, it's pretty much an impulse at 0. All right? Yes? All right. And then if you have actually in general any complex exponential, so a complex exponential will also be an impulse, except that if this is complex exponential with a frequency k0, some frequency. Everybody is clear, by the way, on a complex exponential? I forgot about that, actually. So what is a complex exponential? Anybody unclear? It's okay, it's fine, just let me know. So because this is used all the time. Yes, complex exponential, we're good? Okay, so what's the real part of this? If I take the real part of this complex exponential, what do I get?
Cosine.
A cosine, that's right. And what if I take the imaginary?
Sine.
That's the sine. So sine 2 pi k0 x would be the real part of this, right? So, okay. All right. Now, if you actually stare at this long enough, you go like, oh, you know what? These are periodic signals, right? Like 1 is kind of like a degenerate periodic signal, right? It's constant, but this is definitely periodic because it's a frequency. It's a sinusoid function. So anything that is actually periodic, its Fourier transform is impulsive, like it will have an impulse. Okay, so anything that's periodic would end up having an impulse, and that's very typical. Now the other case is if you have an impulse. So let's say some impulse at let's say at x0. So this is a delta function that is around at x0. Its Fourier transform would be then a complex harmonic with a frequency of x0. So if this is impulsive in the time domain or the space domain, the Fourier domain would then be periodic. So periodic results in impulsive. Impulsive results in periodic. And so there's really this symmetry between these domains. I mean, the fact, by the way, that the Fourier transform, stare at this. I mean, it just had a minus over here and a plus over here. That's, by the way, almost completely arbitrary. We could have picked a plus over here and a minus over here and just defined this to be 4 and this is backward. Like, who cares? It's exactly the same. Okay, you just need to be consistent. We're going to use forward as a minus and backward as a plus, but some other books might have something else. Okay, so there is a complete symmetry between those domains. Whatever you do, like whatever property there is in one domain that affects the other domain, then that's vice versa. And in particular, this situation of being periodic results in impulsive, impulsive periodic. And so what happens when I have a shell function or an impulse train? Well, an impulse train, if you actually stare at it long enough, you realize, oh, it's impulsive. It's made out of impulses. but it's also periodic, impulsive and periodic. So then its Fourier transform should be also impulsive and periodic. And in fact, the Fourier transform of a Shaw function is a Shaw function. So it's a self-transform. Okay.
Is there a missing minus sign under 2 for the complex exponential mapping to the delta function? Should it be e to the minus I 2 pi?
I don't think so, actually.
Okay.
I think you have to derive it. I don't think so, but I might. Let me check. To be confused, but I don't think so actually. You can go and derive it pretty quickly if you just multiply this. I mean, if you want to compute the Fourier transform of this, right? So you just plug in this here. So e to the plus, right? E minus j 2 pi kx 0, and then you can just subtract that, and then I think then you can end up getting this result. So I'm not sure if it's plus or minus, but Ekin, if you can correct me. Ekin is always right. So she doesn't make mistakes.
No, that's not true.
Actually, it's in the book also, so you can also take a look. If you want to take a look, there's a table in the book. I think it's pretty much this though.
Yeah, the table has it as negative in the book.
Yeah, I think it's
negative here.
For 3, number 3, the exponential is negative.
Oh, here it's negative?
Yeah. Yep. In the book.
Yeah, I think
okay,
that's.
that makes sense. Yeah, and for this one, no, right? Or is it?
I think
it could be.
That one is written how the book has it. Yeah. Yeah.
Okay. All right. Well, I'll believe the book. What? Can you hold on a second? Okay, so let's see. Yeah, so some other properties of the Fourier transform. So if you have f of x leads to f of k, then if we have a scaling of, okay, so any scaling of the function in space or time would then result in also the opposite scaling in the frequency domain. So if I have f of ax, then and a would be, let's say, greater than 1, then if I have effectively shrinking of the time domain, I will have an expansion in the frequency domain. And then if I would have a expansion in the time domain, there will be a shrink in the frequency domain. And it kind of makes sense in some way, because if you think of f of x, let's say, being a sinusoid, and so that results in a certain frequency. If I expand if I expand the frequency, basically it becomes lower frequency, right? If I stretch some sinusoid, then it becomes lower frequency. Hence, the delta function would get the frequency will get then close to 0. Whereas if I shrink the time domain, then I would take some frequency and make it higher effectively. So this is the scaling shrinking property. And then if I shift, so this is an interesting property, any shift in the time domain or the spatial domain, any shift in the spatial domain would result then in a modulation in the other domain. So a shift by x0 would result in a modulation of the frequency domain. And vice versa, if I have a shift in the frequency domain, then it would be modulation in the time domain. So any shift would result in some multiplication by complex exponential corresponding to a frequency, that is how much you shift. If you shift by a lot, the modulation would be with a higher frequency. So modulation would result then in a shift of the other domain. So complete symmetry between the two. All right. Now, another important property of the Fourier transform is the symmetry. If I have a real and even sequence, a real and even function, then its Fourier transform would also be real and even. If I have a real and odd function, then its Fourier transform is going to be pure imaginary and also odd. Okay, these can all be derived from, basically from the integral, from the Fourier transform integral, by leveraging those, and you can actually prove them. And I can, do we give that in the homework to actually derive one of them? I don't know.
I don't think so, but
we have other properties.
We have other properties, yeah.
Yeah. But those symmetries are important. So real and even results in real and even. Real and odd results in imaginary and odd. That also means that if you have a function which is just real, not even and not odd, just a function that's real, then in that case, it will have a certain symmetry, and that symmetry will be conjugate symmetry in the frequency domain. So f of minus k would be f conjugate of k. Now, what does this really mean is that, let me just try to draw here. Let me just find another color. Okay, so what does it mean is, if I have, let's say, the axis, and this is k equals 0, then if I have some real function, and this is capital F of k, this is Fourier transform, then the value of the function here and the value of the function at the negative frequency, so the negative and positive frequency, the value of the function is just going to be conjugate of each other's. So f of minus k, so this point over here, will be the conjugate of this point. That means that you really only need to know half of the Fourier in order to be able to complete the other one. There's redundancy from the fact that the function is real. Now, it kind of makes sense from an information point of view, if you think about it, because in general, you would take a real function and compute a Fourier transform that will give you a complex function. But obviously, if you take something on the reals and map it onto the complex, and it's a one-to-one mapping, then if something sits on the real, it has some redundancy, right? Like it doesn't, it's a lower dimensional space than the complex, right? The complex function, it's a subset. And so in that case, the frequency domain has to have some redundancy that represents that lower dimensional space, and that symmetry really represents that. Okay, so you really only need to know half of the Fourier transform in order to complete the other one. So, and this actually has a lot of implication for MRI. And the first implication for MRI is what's called half Fourier imaging. And the idea there is, if we remember, we collect data in the frequency domain, right, in K-space, one line at a time, and then we compute an inverse Fourier transform of the image in order to compute, you know, in order, we compute an inverse Fourier transform in order to get the image. Now, imagine the situation where I collect data. It takes me time to collect the data. So I don't know, we said it could even take 2 minutes to collect all the data. But then if I know that the image is real, I mean, from a certain point of view, I mean, MR images should be real. I mean, why shouldn't they? They represent magnetization. Why that should be a complex values, right? So if the image was real, then collecting only half of the frequency domain would have been enough in order to reconstruct an image. All you have to do is complete the other part based on this part. So this part should be a conjugate symmetry of this part. And the conjugate symmetry, by the way, is represented such that, for example, this point over here should be conjugate symmetric with this point over here. And this point over here should be conjugate symmetric with this point over here. And then pink is my favorite color. This point over here is conjugate symmetric with this point over here. Okay? So I can basically take all the values from the top and then copy them to the bottom and be able to reconstruct the full image. Okay, that's the idea. That's as long as the image is actually real. In fact, I told you though that MR images are not real, but they sometimes can be approximately real, and that that's another detail. But what you could do, perhaps, in the case when it's not real, is collect a little bit more of frequency domain. So collect also this part, for example, and not the rest. And then use it to estimate, use the low frequency to estimate some phase, and then through that you could complete the other part. So it's not completely, you know, that option is still there. And this is called half Fourier imaging, and it's a very common way to speed up MRI. Okay, collect half of the Fourier domain. Okay, any questions?
Yeah, sorry. You were talking about those symmetries. I thought we only have symmetries if the signal is real and even or odd. So how do we know that in K space it's even or odd, or does it not need to be even or odd?
Well, first of all, I said, okay, so actually it's exactly the same. So there's a symmetry. If something is real and even in one domain, it's going to be real and even in the other domain. If some function is real and even, real and odd, it's going to be imaginary odd in the other domain. So if something is real and even in the time domain, it will be real and even in the frequency domain. If something is real and even in the frequency domain, it will be real and even in the time domain. So there's a symmetry there. You know, there's a reciprocity. Does that make sense? If something is real and even and real and odd, I mean, then if I just take the real part, then I should still have some symmetry, but the symmetry would be that I will have conjugate symmetry. So the value on the other side is just going to be a conjugate. So the imaginary part is going to be negative, the real part is going to be the same. Does that make sense?
Yeah, thank you.
Okay, so talking about convolutions again, if you have a convolution between two functions, if you actually compute the Fourier transform of that convolution, it is the same as computing the Fourier transform of one function, computing the Fourier transform of the other function, and then pointwise multiply those two functions together. So this actually can be a very complicated operation, very time consuming. But if you have actually the Fourier transforms, then all you need to do is just the dot product between the two. It's just a multiplication. Pointwise multiplication between those two functions. So this is easy. This could be difficult to compute. All right. In the same way, if we have multiplication in the time or spatial domain, then that will be a convolution in the frequency domain. So any multiplication in one domain will be a convolution. Any convolution will be a multiplication. Again, the reciprocity between the two. Does that make sense? Now, why is it useful is because often to compute this is hard. So what I could do, for example, is compute the Fourier transform of one, compute the Fourier transform of the other. And there's ways to do that pretty quickly. And then I can just multiply those functions together, and that's easy. So there could be some savings, both from an analysis point of view, but also from a computational point of view. And we're going to use this property quite a bit in order to do some analysis on sampling and resolution and all that kind of stuff. Now here's just an example. Let's say I have some system with an impulse response h of x. And I put g of x into that system to get y of x. Okay. Now sometimes I want to create a specific output, and I need to design g of x to produce my desired y of x. So I don't know what g of x, but I know what y of x is. I know h of x. I need to design g of x in order to do that. Okay. If I knew what g of x is, to find y of x is easy. It just convolve h of x with g of x. But if I know what y of x needs to be, and I know h of x, you know, it's not trivial to actually find what is g of x is. Right? That's not trivial. We need to do some sort of a deconvolution, right? Because this is the result of a convolution between these two. But this thing is actually easy in the frequency domain because y of k equals g of k h of k. And so if I want to know what g of k is, all I need to do is I'm going to take y of k and divide by h of capital K. And the result will give me the Fourier transform of g of k. And in order to compute the small g of x, I just need to take an inverse Fourier transform. So that is very easy to do. And the question though is, could there be problems that arise if I do that?
Well, h of k could have 0 frequencies, which basically means it's like zeroing out certain frequencies from the input. And so it's ill-posed to try to reconstruct those frequencies.
That's right. So if h of k has some zeros, then this is ill-defined, like it's just not defined well. So I'm going to have a problem. And you're absolutely right. So deconvolution is not a trivial operation. Okay. So you have to realize if somebody says, oh, just deconvolve the signal. Well, convolution is, you know, can always be done, but deconvolution not always can be done. Okay. Convolution is a lossy operation. If h of k actually has some zeros in it, then you lose that signal and it's just not possible to reproduce it unless you know some other things. Okay. Well, I guess it's already 4, huh? Yeah. Okay. Well, at least I did a few things. Let me just cover this idea of sampling, and then we finish. So okay. So let's say I have some signal, let's say a sinusoid. And the question is how frequently I need to sample this sinusoid in order for me to capture all this information of the continuous function in the discrete representation. And I would argue it's like you know, you ballpark it, and then you go like, oh yeah, it's kind of looks right, like that's looks plenty of samples, because even if I removed this sinusoid, I can kind of see how this is doing, right? Again, I'm waving my hands. What about that? Is that enough samples in order to represent the sinusoid? Probably not, because if I actually sampled every every space like this, I would just get a constant signal, right? Like it would not look like a sinusoid, so that's too slow. So one is fast and probably fast enough. The other one is too slow. So there's probably some optimal or like at least minimum sampling rate that I need to do. And the minimum sampling rate is pretty much, you need a rate that is strictly larger than twice the sample period. Okay, so strictly larger than that. So in general, the rate of sampling needs to be twice the bandwidth of the signal. Now it has to be strictly larger as opposed to being exactly. And the question is like, why? Well, if you think about it, here, this is exactly that rate. So this is the critical rate. So I sample here and I sample here and I sample here, and you can kind of see, oh, it's going to go like between 1, -1, 1, -1. And that kind of looks like this cosine. But the question is, what would have happened if I had a sine? If I had a sine, then I can also say that this is 0, right? This, sine would be starting here, right? This would be a sine, right? Starting at this point. This would be a sine function if this was 0, right? Then if I would sample here, and I would sample here, and I would sample here, and I would sample here, what I would get? I would get zeros. So that's not enough. So being equal to twice the sample per period is not good enough. You have to be just strictly large, faster than twice the period, and that will allow you to see this edge case. If you're strictly larger, then what would happen is that second time you sample is going to be here. The third time you sample, it's already here. The fourth time you sample is over here, and then you can kind of discover that, the shape. So there's no ambiguity. It's not going to be 0. Does that make sense? Okay. So I think, yeah, and this is actually an example of an aliasing phenomena. This is with a camera. So the camera, the rate that is actually collecting an image was exactly the same rate as those black and white, I guess, bars were kind of moving, and so it looks like they're either moving forward or staying stationary, even though they're not. And basically, that frequency of occurrences is aliasing into DC, to a constant frequency because of that. So, and obviously, if you go starting to go slower, then that's not a situation anymore. Okay, so we're going to start tomorrow, I guess, talking about sampling in K-space, because most of you are familiar with sampling in the time domain or maybe the spatial domain, but you have to wrap around you have to wrap your mind a little bit about sampling in the frequency domain, what it really means and how's that affecting. So it's the same thing, but slightly different in the sense that it's a little bit awkward to think of, but hopefully very quickly you'll get used to this. And what we're going to do the next time is analyze the situation of sampling in K-space. And there's actually 2 problems with sampling. First of all is the fact that we're going to sample the frequency domain in a discrete way. The other way is that we cannot cover the frequency domain to infinite frequencies. Because if we sample the infinitely, then it would take us infinite amount of time to collect. So we're going to collect only a finite number of frequencies in the low resolution, and then those will also be discrete. And we're going to basically do an analysis to see what the effect of this discrete sampling and also the finite support of our frequency, how's that going to affect the MR images that we're going to be collecting. Okay. So that is not completely trivial. And so that's where we're going to go and start this Friday. All right. So again, apologize for stealing some of your time and apologize for a little bit being late. So I'll see you all tomorrow.